形体从盖头。
Hello, testing, 1, 2. Okay, good morning to everyone. I realize that all our classes are morning, but this one is closer to lunchtime. Yeah, so let's begin from where we left last time. So, so last time we are stopping at the composite function limit. Okay, should I move here? Hi. So basically, what we have was limit sum a to the function. So you can compute this. Well, you can bring limit into this function. Does anyone know when can you do this? When are you allowed? Are you always allowed to do this? What if the limit doesn't exist? Can you evaluate f at nothing? No, right? Okay, so first of all, this limit of g must exist first. Okay. Second of all, what if this limit lie outside the domain of f? Then f also cannot evaluate, right? Okay, so another thing is it exists, and moreover, if you have limit of f equals to the evaluation of f, what do we call that property? That's the continuity equation. Okay, so meaning that f has to be continuous at this limit point here. So let's say I call this limit point out. Okay, so meaning it's to be continuous at. Okay, so that you can bring the limit. Okay, makes sense or not? Okay, so this is a bit like a generalization of the limit law. Okay, so this is a bit like a generalization of limit law. If you still remember, for example, like the number 9 rule, right? So you can bring this limit of the square root of f x function here equals to limit of x of f, and then taking square root. If you don't like this f, maybe I can change it to g. So then in this case, we'll see that f x is actually square root of gx. Okay. Question? Got question? No? Yeah. So remember that the limit law property here also require that this thing exists. Also require that this point here is defined. Okay, if you remember the limit. Okay, so it's the same problem. Okay, so I left these two questions for homework. Hopefully you have done it. If not, we'll quickly run through it. And let's quickly run through it. Okay, hopefully that you have tried at home. Let me ask you a quick question. If you try at home, if you did mistake or you fail, does it matter? Does it matter? If you make mistake, if you cannot complete answer, does it matter or not? How about us? Are you Margaret? No, Margaret. Who? Felicia. Yeah, Felicia. Okay. Does it matter or not if you make mistake when you do exercises? Yeah, so it's okay, at least try. So you just keep trying. Okay, so just keep trying. Moreover, the solution I gave you in the Moodle actually contain all the steps. So make sure you understand the step. Okay. All right. So let's quickly check these two. Okay. So show that HS is continuous except at 3 and minus 2. Okay. Did you realize that what happened at 3 and minus 2 here? 0. So what thing becomes 0? The denominator. Okay, the denominator inside the sign becomes 0. So if you rewrite this that's right. So this is a very important skill in this class, which is factorization. Okay, so this technique you must master. So if you factorize the denominator, you can quickly see that you have x minus 3 factor and x plus 2. Okay. All right. So which is actually undefined at 3 and okay. So the point here is to prove that all the other points it is continuous. So in this case here, what can you see about this function here? Okay, at least I see two type of basic function here. Okay, one type is the trigo function sign. The other type is what we call the what do we call this kind of function? Rational function. Okay, so there are two type of function here. So you can think of this as a composition. Okay? So we can write x hashtag as only x plus x equals to f before g, okay, where fx equals to sine x, okay, and then gx is the rational function. Anyone know what's the difference between writing h equals to fg and hs equals to fgx? Anyone know what's the difference? Anyone know? So on the first case, this is a same function. Okay. On the second case is the same uh, function value. Okay, after evaluating a number, okay, the output is the same. Okay, so these two actually are equivalent. Okay, to say that two function is the same, it is enough to say that at every point of x, you evaluate to the same value. Make sense or not? Okay, if you want to talk about whether these two functions are the same or not, they are not the same. They are only at the same at one point. Okay, If they are the same at every point, then they are really the same function. Okay, make sense? Okay, so this is the subtlety here. All right. So we need to check one by one. What do we start to check first? Composite function. We need to start by checking g. Okay, whether the limit of g exists or not. Okay, so you look at this rational function. Okay, other than 3 and minus 2, can you compute the limit or not? Can. Okay, because since if you still remember the continuous theorem, what does the continuous theorem say? Polynomial function, trigo function, rational function. Okay, maybe I turn to that page so that you know what I'm talking about. Okay. So yeah. Okay, so please remember this very important theorem here. So whenever you map polynomial function, rational function, root function, trigo function, inverse trigo, exponential function, logarithmic function, okay, these are continuous functions where at every point in their domain, okay, as long as they are defined, they are continuous already. Okay, this is a very important theorem here. Actually, this requires a lot of proof, but we won't prove it, so you need to take it as a fact. Okay, once you see this function, you are very happy. Okay, so you compute limit at any point, just substitution, correct or not? So last week we equate the continuity definition as substitution when you want to do limit. Okay, so this is about continuity. Okay, you don't need to go through the limit law, whatever, or check the point one by one. Okay, so this is after checking already. Okay, we prove this theorem here. Okay, so by let's call it a continuity theorem just now. Okay, gx is continuous at where? At all the point that is not equal to minus 2 and 3. Okay, so this is a complement sign. One set throw at the other two items. Okay, also as a set. So in particular, the limit of x, the limit of gx when x approaches a, where a is in this set of complement going away minus 2 and 3. Okay, as this. So gx can map any point, okay, any point as this. At the same time, okay, at the same time, fx sin x defined on the whole real line. Okay, at the same time, fx is defined on the whole real line. Okay, so again, by continuity theorem, it is continuous on R. In particular, it is continuous at every limit point of gx. Okay, for all n in, sorry, don't use this notation. For every a in okay. Any question so far? Okay, so remember this composite function theorem, yeah? To write down this equation, okay, you need to check the limit of gx first, and then check that f is continuous at this limit. Okay, so this is what we did here. So we decompose h into f and g. Okay, we check that this g is continuous and the limit exists for all the points it defined. Okay, and after that, we check that our f is also continuous, okay, at all the point that you get from this limit of g. Make sense? Okay, so this is the only strategy for this. Make sense? Question? Got question? Please ask question. You don't say you are shy. If you are shy, your marks will disappear. You don't learn, you don't. So please ask here. So when you come to lecture, right, you can think of it as like a one-to-one. Only you and me. Okay, whether what I say you understood or not. If you don't understood, you should quickly feedback to me so that I can know what to add on. Okay, so far question. If you cannot ask question at this time, you can leave to next lecture, or after class you can put into the forum as well. Okay, or message me. Okay, anytime you should ask. Okay, there's no time that you can miss. So I have these 14 weeks with you. So please make full use of this 14 weeks. Okay, anytime you can approach me. Does that make sense? After 14 weeks, I don't care about you. Okay, I'm not your lecturer. Okay, so within this 14 weeks, please try approach me. Okay. Okay. So far, so good. Okay, let's look at the next one. So the next one is a little bit tricky here. Let's duplicate this here. Let's remove everything else. Okay, let's do this one. So this function, I'm not sure you still remember that last week I derived with you. Okay. Whenever you get this square root of 4 minus x squared here, there's a quadratic hiding inside the square root. What does these points satisfy? Okay, so this would imply that if you play a bit of algebra here, what you see was kind of like a circle equation. Okay, it's like a circle equation here. In particular, this is a radius of what circle? Circle of radius. What radius of this circle is? Anyone know? Pythagoras theorem, you should remember. A squared plus b squared equal to c squared. So the hypotenuse is the radius. So the c squared here is 4. Okay, so the radius is 2. Okay, so this is the circle of radius 2. Okay, so from last week, right, you realize that when the circle of radius 2, maybe you try this. This is radius 2, the radius 2. Okay, but are we taking the full circle or not? No, right? Okay, so which part of circle we are taking actually? Okay, we're only taking half of it. Okay, we're only taking half of it. So which half? Actually, is the upper semicircle. Okay, so we are just taking the upper semicircle. Why? Because the gx we care about is just positive. Okay, so the positive is lying at the upper half plane. Okay, so this is the upper half plane, and this is the upper semicircle. Okay or not? Okay, so in case if you want the bottom one, how should I write down the bottom one? So it should be gx equals to minus square root or minus. No. Okay. So from this picture, you can roughly guess what's the domain already. Okay. Can you pick domain outside here or not? Now no graph there, there's no graph there. Okay, so you need to ask yourself what's this 2 point here? Okay, what's this 2 point here? So this 2 point is characterized by one thing, right? Which is this that's why I asked you to label. This 0 is pretty important. Here y equals 0. Right? So gx equals to 0 in particular. Okay, so when gx equals to 0, Yeah, good. So you have 0 equals to square root 4 minus x squared, which is equivalent to x squared equals to 4. Okay, so how many numbers, how many kind of numbers square you can square to 4? Either you are 2 or either you are minus 2. Okay. Make sense? Okay, so there's maybe there's a problem here. People would just okay, will just write like this. Okay, which is not true. Okay, you actually need to solve by plus minus 4. Okay, so this is the subtlety between square root function and finding a square. Okay, it's a bit different. Okay, square root function we only define for the positive. Okay, so this 2 is 2 and minus 2. And you realize that if you put anything in between 2 and minus 2 into this square root function, it will be always positive. Okay, because you always square to something less than. So let me write down what I said. So for any x in between 2 and minus 2, sorry, minus 2 should be on the left. So minus 2 here and then 2 here. Your 4 minus x squared, okay, should be less than uh, sorry, should be greater than or equals to greater than 0. Okay. Okay, so other than that, what do you need to know? What do you need to know? Yeah. So it is defined. Okay, so G is defined. Yeah, the interval of close interval in particular. Okay. How about continuity? So at least I can see again. I can see two basic functions happening here, right? Okay, one of it is square root. The other one is polynomial. Okay, so again, you can rewrite this. So we could rewrite. Let's say h f. H is the square root function, and then f is the 4 minus x. Okay, make sense? Okay. So now let's not write down the full argument. I left you to write down full argument like what I wrote just now, but let's quickly discuss. So within minus 2 and 2, polynomial defined or not? Defined. Is it continuous? Yeah, because it's defined there, so it's continuous there. Okay, so by continuity theorem, f is continuous at minus 2 and 2. Since f is defined there. But if you look at all the a in minus 2 and 2, and then if you look at the limit, right, of fx going to those two numbers, what can you get? What could you get? Do you have an idea? You can, because it's continuous there, right? You can really just do fa, right? Okay? Because it's continuous there. But if you put all these numbers from ranging from minus 2 to 2 into this formula here, what do you get? This is equivalent to asking what's the range of fx. Okay, what's the range of fx? What's the range? Okay, so you see, this is a first week material. So we are asking about the range, okay, of fx. So your f here now we restrict only to minus 2 to 2. Okay, so what's the range? So let's say the codomain is, what's the range? Sorry? 0 to 4. So let's check. Is it 0 to 4 or not? Okay, let's check whether it is 0 to 4 or not. So if you put minus 2 into it, okay, well, let's graph it, right? So from last week, we should know how to graph this guy here. I mean, from first 2 week. So first you have the basic shapewise x squared, right? Okay, but this is a negative x squared. Okay, negative x squared, what should you do? You should reflect it. Okay, you should reflect down, right? Okay, but what happened? But you go to plus 4. What does it mean by plus 4? You need to move all the graph up by 4. Okay, so let's move it out. Okay, so let's move it out like this. Okay, so here is plus. Okay, so now the domain we only restrict to -2 to 2. So what happened at -2? What happened at 2? What's your range? What's your image? Both of them are 0. Okay, so actually this x-intercept here is -2 and 2. Okay, so anything in between -2 and 2, it is from 0 to, okay, not make sense, huh? Okay, so actually the maximum point, the highest point, right, of this graph, right, is in the happening at the middle of this domain, which is 0. Okay, not okay. But so now the range is this. Okay, so the range is this. So the limit of fx can reach this range here. Okay, can reach this range. So the next question you should ask is, does h continuous at this point or not? Yes or no? Because your square root x defined at all the positive real number. Okay, so this is just part of it. Okay, so next step and then next step. So since h is defined at 0, 4, the interval 0 to 4, and h is continuous. Okay. Again by continuity. Okay, so altogether the whole function is continuous at -2 to, so hence by composite Debit theorem, and no, not h anymore. We call it G. Okay. G is continuous all the way from. Okay. Any question? Question? Okay. So in this class, especially in my class, please don't copy. Please don't copy. More importantly is you have to understand what I say, or check that whether what I say makes sense or not. Okay. Because I will always give you the notes after the lecture, so you don't need to copy. So you need to understand how to read my lecture. Okay, that's more important. Okay, you don't need to copy. Last time I met one yesterday, and I met one advisee. I'm not sure your department got this advisee system. Do you have it? It's like a lecturer assigned to some students, so that these students can meet a lecturer regularly to ask questions or what. Do you guys have it? No, no. Okay, we got it from the MAT department. We got it. So one advisee talked to me. It's like, I don't understand this lecturer accent, so I just copy. It's a linear algebra course, like your linear algebra, maybe a bit advanced, but the content is more than that. So he copy. He say he don't understand what lecture is talking about, and also teaching. So he showed me. He asked me, what is this? So when I read, I say, no wonder you don't understand, because you already copy wrong. You understand or not? Because in mathematics we have a lot of notation. So you subscript, superscript, the difference is very big. So sometimes subscript, sometimes superscript. So you don't know what you are writing. Okay, so most importantly is you understand what I wrote down first, and go back. You have time, you can copy also. Okay, otherwise you just copy, you don't know what I'm talking about, you copy wrong, you cannot understand also. Useless. So what's the point of copying? Well, no point. Then there's no point of copying. Understood? Okay. Okay. So before we go to the next section, right, we want to finish this intermediate value theorem. Okay, so let's talk about this intermediate value theorem idea first. Then we will see what can we do with that. Okay, so let's draw some graph here. Okay, so intermediate value theorem was concerning about one problem here. So let's say I know my function take value here, let's say fb. Okay, let's say here there are two x point a and b, and then I evaluate my f at b, and then I evaluate my f at a. So the question is, if I get another point, okay, between let's say call it z here, okay, fa and fb, can I get my function to hit this guy or not? So the question is, does there exist a c such that fc equals to z? Okay, so this is the question. Okay, can we always do that or not? Okay, obviously this is not true. This is not true, right? For example, if I create a function like this, okay, the Heaviside theorem that you will see before, like this, particular like this. Let's say I don't want to define my function as c, then you cannot find it anymore. Okay, there's no chance of doing it. Okay, but if you want the c to exist, that means this fc here should be one of your output or your range inside your range. Okay, and then you can ask a similar question: can I do it for point between fp and fc? Is my f gonna hit it or not? Okay, in this case also no. The answer is no. But let's say I modify this f a little bit. Yeah, let's say I modify this. Maybe I add it in like this. Okay, got. Okay. Then you can repeat this process infinitely many times. Okay, infinitely many times. Okay. So what you can see here is a bit like a continuity problem here. Okay, if your function is continuous, okay, you can hit any y value in between two y value that you get. Okay, does it make sense or not? It makes sense. Okay, yeah. If you cannot achieve, it's like the graph break. Okay, there's no point. Okay, so it will break. Okay, so this is a statement. Let f be a function defined on closed interval, and an n a number between fa and fb. Okay, the two numbers that you can achieve. Okay, if f is continuous on this closed interval ab here, then there exists at least one number c in between here, such that this fc will be evaluated to this. Yeah. Okay, so this is another problem about continuity, which we call the intermediate value theorem. Okay, so what is the intermediate? Intermediate is like middle, right? Okay, middle. So these are all the intermediate values. Okay, that you can. Okay, so let's see how we use this theorem here. So now we want to show that the equation x minus cos x equals 0 has a solution in between x equals 0 and x equals to pi 2. Okay. So what does it mean by this equation have a solution? So you need to find an x, okay, such that this equation holds. Okay, or another way to put it is we want to show that exists an x such that fx equals to 0, where fx equals to sine minus cos x. So we put it in a more familiar form to our function theory. Okay, more familiar form. All right. So you want to hit 0. Okay, you want to hit 0. So you want try to use intermediate value theorem. So what's the condition? Okay, the condition is pretty important here. So let's highlight what's the condition. If, where's the if? If here. Okay, if f is continuous, then at this open interval, close interval here. Okay, then you will have a number in between this open interval such that fc equals to some number. So if you try to compare what we had just now, right? What's our situation now? Can you compare quickly? So our f is x minus cos x. Okay. What's the n we care about? We care about. We care about. Remember? Yeah. What's the n we care about? What's the n we care about? Here, 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 here. What's the n we care about? 0. Okay. This n we care about is 0. Okay. And then you want to find solution in between 0 and pi over 2. Okay. Solution in between 0 and pi over 2. Okay, we have this object, but we haven't checked whether it's continuous there or not. Okay, once we check that, then this theorem will give me the answer. Okay, understand? So what's the thing we left to check here? What's the thing we left to check here? I think there's one more thing to check because this n got property. This n, we cannot simply check for all n. This n has to be a number in between fa and fb. Okay, let's check this. Okay, this one is easier to check. So what is f0? Okay, what is f of pi over 2? So f0 is 0 minus cos 0, which is what? Cos 0 is what? Remember the graph? You start from 1 and then go up. So it's 0 minus 1, which is minus 1. How about pi over 2 minus cos pi over 2? Okay, cos pi over 2 is 0. Okay, so you left with pi over 2. Okay. So this fa is 0, and then cos pi is fa is minus 1. Okay, minus 1, and then fb is pi over 2. Okay, good. So 0 is indeed in between fa and pi over 2. Okay, so the next thing we need to check is continuity. Okay, continuity. Right. So how to check this continuity? Okay, if you still remember, we have a similar theorem for continuity like a limit law. Okay, you can compute limit of a sum of a function by separating them out. Okay, similarly, if you know that two functions are continuous, okay, the sum of them is continuous. Okay, scalar multiple of a continuous function is also continuous. Okay, what else? Quotient, product. Okay, so it's a very similar theorem you have here. See this one. Okay, this is also very important theorem. Okay, once you know two functions continuous, you can combine them in this way. Okay, still continuous. Okay or not? Okay. So please keep these in mind, yeah. So in exam, not in exam, at least in this quiz, okay, at least in the quiz, when you use the limit law, you should specify. Okay, you should specify. You can specify down to which one you use. Okay, because in quiz you have time, right? Okay, and then you do it on your own, you got notes with you. Okay, so please write it clearly. Otherwise, we might deem that or you copy from somewhere else, you copy from others. Okay, so write down every step why this is true, why. In exam, maybe we will be a bit loose, or maybe we will provide the table. It depends. Okay, but quiz, please write it as clear as possible. Okay. So in this case here, we are in the case of sum, right? Because it's a polynomial plus a trigo. Where is it? Yeah. Okay. So we know that the x is defined at everywhere. Okay, in particular 0 to power 2. Cos x also defined everywhere. Okay, in particular 0 to power 2. So their difference is defined on this domain. Okay, so it is good. Okay, so not that. X minus cos x is continuous on the interval 0 to pi over 2. So by intermediate value theorem, so let's call it IVT, let's abbreviate it. There exists C, okay, in the region of 0 to pi over 2, such that FC equals to 0. Okay, FC equals 0 meaning what? There exists a solution C minus cos C equals to 0. Okay, then we are done. You might be weird, huh? Hey, you haven't find what's the C. I say we don't care. We don't care. We only care about existence. Okay, for now we don't care. Because it's not always true that you can just apply some algebra, you can find the C. It's like normally when you solve like quadratic function, you got a quadratic formula, right? What is the quadratic formula? B squared plus minus square root B squared. Sorry, what's the quadratic formula again? Huh? 2b, yeah. Start from 2b. What's the quadratic formula? Negative b, good. Negative plus minus square root b squared minus 4ac over 2a. Okay. It's not always true you got this kind of formula. So maybe later in your later year you will learn something called numerical method. Okay, or numerical solution, where you need to do some iteration to find the solution. And that solution will converge to the actual value, but maybe it's not even the right value also. Okay, so it's not true that always you can find a fixed solution like roots. It's not as nice as a quadratic equation, okay, where you can always find as long as the b squared minus 4ac is greater than 0, you can. But this is not always true. Okay, so in real life, right? What we care more is about existence. Does it have solution? No. If God, maybe we can go and find it. Find it. If no, no need to find anymore. Okay, no need to find it anymore if this is not happening. Okay. Okay. If I want to right, maybe I could add like this 0 is squeezing in between our 2 and -1. Okay, this is the first thing we check this one. Okay, so that's why this is called intermediate value theorem. Okay. Obviously, this n must be squeezed by some function value f. You don't go and ask some point outside, right? Okay, you don't go and ask some point outside the range of f, because if it's at the outside at the range of x, you might not hit it anyway, whether it's continuous or not. You won't hit it. Okay, so the point here is if I have an n that's squeezed in between my range, some range, can I hit that n? Okay, so far any question? Any questions so far? Yeah. Question? No. Okay. All right. Let's continue. Okay. Next. Next is limit at infinity. So previously, what we care about is a, just a random a, which is a real number. Now, let's talk about x going to infinity. So what does it mean here? So you can think of your real number line going to the right. Okay, going to the right. Okay, infinity. Okay. So how about draw a picture? Draw a picture here. Okay, so your x is going to infinity like that. Okay, so you want to see what happened to your function. Okay, how your function grow. Okay, when x go to infinity. Okay. So let's say your limit is going to equal to L. That means that when it goes to infinity, okay, it will like try to hit some, actually we call it y equals to L line. Yeah. Then we'll say that the limit of fx is L when x go to infinity. So these are the three possible cases here. Okay, so either you approach from bottom, from top, or you can alternate around this line here, but you will eventually get very close. Make sense? Okay. It's possible that you can touch it, but the nice thing about limit is not touching. Okay, even if it doesn't touch, but you get really, really close. Does this challenge your intuition or not? Does it? No. Why? Why? Why do you think that it makes sense? Never touch or still close. Is it possible? Possible? How?
So infinite numbers, so it always stays close.
Okay, very good. So there's a point here is you need to understand. Okay, maybe you think about numbers like 1, 2, 3, 4, 5, 6, 7, 8. It's like discrete. There's some distance. But how about in the between of 1 and 2? There's a half. In between of 1 and half, power 4. So there's like a lot of number in between them. Actually, infinite number is not enough. There's some property, what we call a dense. It is dense. The number is dense. Infinite is not enough. Because 1, 2, 3, 4, 5, 6, 7, 8 also infinite. But there's a distance between them. But our real number, there's a very special property. It is dense. Very close. No matter how close between two numbers, you still can find a number between. So meaning if these two classmates, right? Okay, you see, there's a distance here. Okay, you can see a very clear distance. If no distance, it's a sexual harassment. Okay, so there's a distance here. But real number is different. So I found a distance here. I can put another guy here. Put another guy here. These three persons still got distance from each other. I can still put it in. I can keep putting in. This is a big problem. Why can you do it? Okay, if you think of it, the real life, right? Not you put it in, fill up already. No space. But real number is dense. Okay, so that's why we have this idea of getting very close but don't touch. Okay, getting very close but don't touch. Okay, really close. Once when you zoom it in, there's still a distance. Every time you zoom it in, there's still a distance. But it still get very close. Okay, so this idea is very intriguing. Okay. Similarly, you can go the other side. Okay, you can go to a negative infinity side. Okay, you can go to the left-hand side here. Okay, to see what happened to your f. So let's say if you want to do this, what you gonna do? What is your first instinct to do this question? Do you have any instinct or not? So okay, maybe one of your instinct is like substitute. Substitute first, but you get infinity over infinity. So what does it mean by infinity over infinity? Meaning the numerator will go infinity. The denominator will go infinity. So you take a very big number, divide a very big number, what do you get? Alicia, what do you get? A big number, divide a big number, what do you get? Guess what? That's a number. You sure? It's a number. Okay, maybe it's a number. So this number is big or small? It depends. Right. Okay. For example, a million over a million is 1. 10 million over a million is 10. A million over 10 million 0. So there's a lot of possibility could happen here. Okay. But I think we got some trick from limit law, right? What's the trick? Actually not limit law. We can replace this function. How? What's the technique? What's the technique from limit law?
It is easier, like subtract x in the top and x in the bottom.
Correct. Okay, so we just replace this by a similar function. Right, we multiply by 1. So in this case here, we multiply by 1 over x over 1 over x. This. Like this. Okay. Is it enough? Let's see. Let's see if this is better. Everyone okay with this technique here? We are multiplying by 1. Okay. So this is 1 over x plus x. Is it? Yeah. Okay. But in this case, what happened? The top is 1. The bottom 0 plus infinity is infinity. So it's 0. Okay. So the bottom go to infinity. Okay. So what I demonstrate here is not that limit law, local theorem applies in this kind of infinity limit case. Okay. So whatever you learned before, you can apply the law again. Okay. Obviously, we have to prove it, but this is not a class about proving, so you have to use it. Okay. Or not? So in this kind of limit, previously we only care about a finite a. Okay. But now in this case, we replace by infinity. Still, you can use those things. Okay. You can use those law we learned just previously. Okay. Or not? Does it make sense? Yes. Where do I get the 1 from? You mean this one? This is x over x. So it's 1. Yeah. Makes sense or not? So this is what we do. We multiply top and bottom by 1 over x. Okay, makes sense? Okay. Because these two functions actually is the same when x is away from 0. Because we care about x go to infinity. So we are caring about x is not 0. So this function will be equal. Okay, so if you want to be precise from what we have learned last time was x over 1 plus x squared equals to 1 over 1 over x plus x when x is not equal to 0. Okay, but this is okay because we are not caring about point near to 0 or even at 0 because well, our point is very far away from it. Okay, no? Question? Any other question? Good question. Okay, good question. Any question? So far? Happy? Happy? Okay. Okay, if no question, right? I already give you this hint here. So there are a few examples you should try out. Okay, they are really same exercise we did for the limit when x go to some finite a. Okay, so I'll try and do it. And then I'll provide answer. Okay, you could check later. Okay. Okay. Okay, so then we will take a break. After a break, we will learn about this horizontal axis. Let's break until 11:03. If you want to go toilet, maybe you can come and take attendance from me first before you go. Because maybe you will stay long outside. Then I might mix you later. For those who are here, maybe I just take attendance. Hang Xi He, yep. Chen Le Tian, Chen Le Tian, Chen Le Tian, Chen Rui Yang, Chen Ruo Shi, Chen Shi Man, Chen Yinan, Chen Yutao, Yutao. Yutao, are you not here on Friday? Friday. Yeah, Friday. Last Friday. Do you absent? You absent, right? So what's the reason? Cannot hear. You go for toilet? Okay. So make sure you next time you come and take attendance on Friday. You go to the toilet? Okay. 陈奕哲、戴立文、邓瑞阳、方哲瀚、胡佳来、何嘉诚、胡佳怡、黄奇军、黄毅清、季俊义、孔相思、雷艺玲、李冰珍。Hey, I remember you are here last Friday, right? Yeah. Not sure why I put absent here. Okay. 李佳棠. Sorry. Yeah. Where's your friend? Not sure. Okay. 林浩云、林文琪、刘汉祥、刘汉祥、刘汉祥、刘俊义、刘俊义，sorry，刘俊杰，sorry，讲错了，sorry，刘新阳、卢旺达，卢新月、罗玉恒、马义田、马义田、马义田、苗冰城、苗冰城啊，you，OK，倪浩然，Desmond Tan，Desmond Tan，OK，for me，for me here，OK，罗琼义，罗琼义，OK，安英杰。Islamova, Islamova. Oh, I think this guy is like never. Gopagani, Pater Suraya, Arianto, Isham, Daniel Fran, Hashim. Hashim is here or not? Bin Yusuf Hashim. Madia Fran also. Aaron, Brandon, Alicia God, Gunakanti, Margaret at the back. Hassan Khalid. Jahil, I think not here. Jahil, Javed, Kiat, Mo, never appear this person. Gabriel, back. Gabriel, this one Gabriel. Okay. Jeffrey, okay. Purity at the front. Chen Fan, He Yating. Okay. Are you just join us? You just join us? Are you in the Moodle yet? Okay. Okay, all the note will be uploaded. Hu Wei okay. Hu Hongliang. Okay. So you also just join us? Okay, are you in the Moodle yet? Yeah, so all the notes are uploaded there. Okay. I miss you.
Also just joined.
You just joined? What's your name?
Javed, Kashif.
Oh, you are Javed. Okay. So you are finally here. Why are you so late? Visa problem. I see. So are you? I think you are not in the Moodle yet. Okay, so I will enroll you. Please do revision on what we have done because you have missed classes. So I put up the recording notes. Yeah, so you can revise it. So where are you? Enroll. You are. Yeah. Where are you from? Zambia. 100.
No,
Wait,
09.
sorry, 09. This one. Yep.
Okay.
So you can check. Okay. Yeah.
Yes.
Sure. Where are you? Left hand.
View.
Handset.
Yeah.
Okay. Left hand. Okay, yeah. Okay. Sure. Anyone just come? You just came late? Asim. Okay. Okay. Let's start. All right. Recall that last time we talked about vertical asymptote. Recall a very standard example. One example you should remember was the tangent x. Tangent x function here. There are two vertical asymptotes, okay, where this function shoot off to infinity. Okay. Well, I mean, like if you consider all the periodic version, there are infinitely many. Yeah, but let's restrict to this minus power 2 and power 2. Okay. So how do you obtain these vertical asymptote, okay, from algebraic equation? So it is by checking limit of x2. Maybe in this case, we could write plus minus pi over 2, okay, of tangent x, which is equals to minus pi minus plus pi. Correct or not? Not true, not true. So I think we need to put more. I guess this is not true. So let's write down one of it first. So if I go from the left hand side of pi over 2, Okay, so meaning going on the left side, coming from left side, okay, to power 2, what I get is infinity. And if I go to minus power 2 from the right side, okay, so this is a plus side. This case here, we get minus. Okay, so far so good. Okay. 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 So in this case, we will keep approaching infinity, but we won't cross this x equals to pi over 2 line. Okay. Okay or not? Okay. We won't cross. So if you imagine if I cross, what could happen? If I cross, then your limit is not infinity anymore. You are some finite point. Okay, so it will never cross. Now we will turn to define what is a horizontal asymptote. Okay, so meaning another very good example to keep in your mind is also tangent x, but it's the inverse of the tangent x. Okay, so if you take the inverse of your tangent x, okay, you will get something like this. Okay, it will approach two horizontal asymptotes. Okay, one of them is y equals to power 2, the other is y equals to minus power 2. So you could see that the role of this infinity reverse. Okay, so if you take x to infinity of a tangent inverse x, you get power 2. But if you go to limit of x go to minus power 2 of tangent, go to negative infinity of tangent arctangent x, you get minus power. Okay, so you can see that the role of infinity and the finite number has changed. Okay, so one of them define vertical asymptote, the other will define what we call the horizontal asymptote. Okay, make sense? Okay. So let me ask you another question. Is it possible that this is infinity, this is also infinity? Yeah? Is it possible? Both these two is infinity. Is it possible? Can you think of a function that does that? Huh? I hear something. Can you think of an example or function that when x goes to infinity, the limit is infinity? Can you think of what function doing that? So when you go far in x, y also go very far. It's a very simple function. Y goes to x. Because x go to infinity, y also go to infinity. Very is exact. I mean, like almost easy example to do that. Okay, polynomial in particular. I mean, okay, polynomial function who does that. Okay. In that case, we will pick one question to do a very interesting one. Let's pick one. The other I will left for exercise. So let's find horizontal and vertical asymptote of this graph. Okay, so well, there are two things you need to find, right? Okay, there are two things to check here. So let's write down the criteria again to recall. What do we need to do for horizontal and vertical? So here is horizontal one, here is vertical one. Okay, so for horizontal one, we want to find L such that limit of x to either class of infinity of fx equal to L. Okay, we have to find some L. Okay, how about vertical? We want to find A such that when limit x go to A of x, it will either go to plus minus infinity. Okay. So these are the role played by this infinity and number, and then which one determine the horizontal asymptote orbit. Okay. Okay, so well, I think most people don't understand max or hate max is because they don't have picture in their mind. Okay, so you should keep picture inside your mind. Okay, what does it mean by limit to plus minus infinity fx is equal to L? Okay, so you should think about like when x go very far, either to the left side or the right side, it should hit something, get very close, and get very close to some number. How about the vertical case? Okay, when your fx, okay, get very close when x goes to a, okay, it shoot up to infinity. So that's why you got this vertical line here. Okay or not? Okay. Does it make sense? Okay. Yeah. So just now, in the horizontal asymptote case, you got something like this, right? It will work as well. Can I do this snake thing on the vertical side? Why not? Good. That's not a function. You will miss the vertical line test. So that's why this situation we won't consider in the vertical case. Okay, very good. So the only case for vertical asymptote is this kind of case. Either you approach from the left or from the right. There's no like the same approach. Yeah, but horizontal it will happen. Yes. Okay, as well it get very close. All right. Any idea on how to solve these two? Maybe the horizontal one is easier. First, in this case, because we just do it, so maybe the memory is still fresh. But if you just straight away substitute, I do the stupid way. What do you get? Again, you get infinity over infinity. Okay. Anyone want to use L'Hopital rule? Please don't. I haven't teach derivative yet. Okay. No L'Hopital rule yet. Okay. So what we're gonna do is again replacing this function with a simpler function. Okay. So in this case here, there are a lot of polynomial, right? So I think there's only one thing you could do for now is just divide by x. Okay, just divide by x. So if you divide by x, how many x you want to divide here? How many x you want to divide? So let's compute for one of the infinity first. Divide by x. So to divide by x, inside square root, you should divide by x squared as well. Okay, this one, everyone okay or not? Okay, you put the x into square root, you put become x squared. And then this one become like this. X minus 1x. And all together, what do you get? Square root 2 plus 1 over x squared over x minus 1. Okay. So you could imagine that 1 over x squared, when x go to infinity, what happened? It decay. Okay, go to 0. 5 over x as well, also decay. Okay, 5 over x squared decay faster. So these two terms here, we are using limit law, by the way. Although I didn't write it down. So this is going to 0, this is going to 0. So only the constant will stay. Okay, the constant function. So altogether, what you get? Square root 2 over 3. Okay. How about go to negative infinity? Is the similar calculation work? Similar calculation work or not? If you put negative infinity, you go to the negative side. 1 over x squared still decay. Okay. Well, I mean, like, if you still cannot understand what I said, you really have to draw. Okay, 1 over x squared looks like this. 5 over x, actually, this is a minus 5 over x, huh? So it's something like this. Okay, so to the left side, you also go to 0 as well, because you get really big inside your denominator. So 0, 0. So this is the same answer if you compute the other direction. Okay. Make sense? Yeah. Okay. And how about the other case? So this is the only thing we can compute. Can you guess where this guy can go to infinity or not? Okay. When x go to a fixed value a. Okay. Maybe you can study the numerator. Where does this numerator go to infinity? If I fix any value a, it is just a finite value because it's continuous. Okay. So numerator can't really go to infinity at a finite value. How about denominator? What denominator? We like to check when the function is not defined, right? When we say the function not defined, what do we mean? You divide by something 0. Okay, so meaning near the 0 point, right? Your quotient will get really large. Okay, will get really large. So 3x minus 5. Okay, you look at 3x minus 5. When is this 0? When x is equal to 5 over 3. Okay, so if you put value close to 5 over 3, this 3x minus 5 will get very small. So you are divided by a very small thing. So you get very large. Okay, okay, so not that. Limit x to 3 over 5. Okay, what is it? Okay, actually you have different answer, you know. Going from left and right, there are different answer. Okay, going from left and right, there are different answer. Why? Okay, why? Numerator actually doesn't matter because after square is positive. So after square root is still positive. But the problem is denominator. Okay, the problem is denominator. Okay, so think about it. Let's think about it. So let's say 3 over 5 is here. So what is larger than 3 over 5? Maybe 1. Right? So I look into 1 here. Okay. How about half? Is it less than 3 over 5? I think so. Okay. Because 3 over 5, 0 over 6. I mean, sorry, 0, 0.6. So if you substitute 1 into this sign here, what do you get? Here. So if you get from the positive side, you get 1, right? 3 minus 5 is negative, huh? Wait, let me see. So if you put 1 here is negative, does it make sense or not? Negative. So if I put half into it, what do I get? 3 times 1, 2. So negative. Okay. Um, what do you think? What's going on here? 3 times 1 minus 5. Okay, so should we plot this out? I don't think we need to plot it. So, okay. So let me write down something here. Let's do step by step. That 1 over 3x minus 5. Okay. So note that square root 2x squared plus 1 is always greater than 0. Greater or equal to 0 actually. I don't think it will hit 0 because there's no negative 1 you can get from 2x squared. How about the bottom? How about bottom? What's the behavior of this bottom here? Sorry?
Should be not 0.
Yeah, you want it to be so for this function to be defined, you want this function to be I think I know what's wrong here. Should be 5/3, right?
Yeah.
Yeah, so this point here is a useless point because it is continuous there. Okay, so uh, that's why. Okay, so that's why. So we should care about 5/3, not the 3/5. Okay. So for example, if I put 2 here, and then versus I put a half here, right? So half here is a negative, okay? Negative 7/2. But if I put 2 there, what happens? So 3 times 2 minus 5 is 1, which is greater than 0. Okay. So what you notice here, if you put more value from the right or left, you will notice that if you approach from the right, this limit is positive, going to positive infinity. The other side will go to negative infinity. Okay. Very small negative number. Okay, on the right side, very small positive number. Okay or not? Does it make sense? Okay, so if you go and take your GeoGebra, you can take out your GeoGebra and then plot it. You get this graph here. Yeah, so this is the graph. Okay, okay, so this is the graph. Okay. So the blue line is the graph, and then the red line is the horizontal asymptote. Where's the vertical asymptote? This one? He doesn't include. Let me include it. Here, this is the vertical asymptote. And then this point is 5/3. Just now we picked 3/5, right? Is here. So that's why from left from right also negative. Okay, just now we picked the 3/5 is around here. Okay, so that's why no matter left or right, we pick very close to this point is still negative. So makes sense, huh? Yeah. Okay, but it's continuous there, so no need to care about left and right. But here is not continuous. So in particular, this left and right is different, and then also go to infinity. Okay, happy? Question? Question? No. Okay. So we're gonna leave this continuity section. We're gonna enter derivative. Okay, so we're gonna enter derivative. Still a bit away to lock it down, so you could wait for a while. Okay. Right. Let's talk about derivative. So what's the idea of a derivative here? So let's talk about idea of derivative first. You will see this derivative in various form in this class for now. And then next up, we will chapter 3 will spend times doing technique of derivative. Okay, for now you will see a different various form how we interpret derivative. Okay, so this is the first idea of derivative. So the problem is I got a graph or a curve. Okay, a graph. Okay, we want to draw something called a tangent line. Okay, tangent line at the point. Okay, so tangent line meaning this line only touches this point once. Okay, only touches this point once. Okay, only touches this point once. Okay, so how do we get this line actually? Okay, so one way to get this line is like the way we thought about was we look at the what we call the secant. And so how we construct this line here. So this is a definition, right? So how we construct this line is we look at all this secant here. Okay, so meaning let's call this x1. This one is x2. Or how about we call this a, and then here maybe a minus h. Okay, so meaning this distance here is h. Okay. Obviously, we got the fa here, and then here is the fa minus h. So we could consider a smaller h. Okay. Smaller h. Okay, even smaller h. Okay. So can you observe something? So there's like a sequence of secant. And there's a bunch of secant. And then how we define this tangent line is the limit of the sequence until this h is 0. It's like coincide. Okay, so let me write down the limit here. So, okay, so this is actually defined by this gradient of this line here. Let's call this gradient of, do we have a special name here? Maybe I can follow what's the notation inside your notes. What do you call it? M tangent. Okay, let's call it M tangent. So we define this tangent line to have this gradient to be the limit of FA minus FA, let's say minus H here, over H. Okay, or this H is coming from A minus H. Okay, or actually we can put a plus H here. Okay, plus H here because we could also consider from the right. We could consider from the right. Because if we define it as a limit has to be true from the left and right. Okay. So these two sides of limit must coincide. Okay, makes sense. Okay. So here is a precise definition of tangent. Okay, usually people tell you, oh, tangent touching one point, touching one point. What do you mean by touching one point? Okay, what do you mean by touching one point is because this secant here was taken with this limit of h go to 0. So the other point is like get very close to x. Okay, so you see, this is the intelligent or the cleverness of this using the use of limit. Why? Because this is like not defined at 0. This function not defined at 0. Because if you substitute h is equal to 0, you are dividing by 0. It's not defined. But the limit is. That's what we want. We don't want to evaluate at h at 0, but the limit as is good. Does it make sense? Okay, so this is the first use of limit already. We don't care about this function. You can see that this is a new function or not. We build a new function using f. Okay, so this is a secant function. Okay, the gradient of the secant in particular. Okay, is everyone familiar with this gradient? In your high school, did you learn this? I think this one you need to recall. Y1 minus y2 over x1 minus x2 equals no. Okay. Yeah, this is what I'm writing down here. So y1 is one of the FA, y2 is another f of something else, and then the bottom is this x1 is the one that realized this y1. Okay, x2 is the one that realized y2. So there a minus h, so you get h there. Okay. Maybe a bit of sign different, but we don't really care. Okay, and then this is actually a limit of this gradient. Okay, so the limit of this gradient approach to something. If that thing exists, we call it the gradient of a tangent. Okay, for now, everyone okay with this idea? Okay, so derivative always start with this limit of secant. Okay, gradient, secant gradient. Okay, gradient of the secant. Make sense? Okay, so next up, we will use this gradient to build our line. Okay, so let's see how we build the line. Now, okay, let's see how we build this line. Oh, there's a solution for this one. So let's start from here. So find the equation of the tangent line to the curve for y goes to 3 over x. So is everyone confused with this usage of curve? Usually we call it function, now we call it curve. Anyone confused or not? Anyone confused? So it's a function, but after we sketch it, it looks like a curve. Curve is like a one-dimensional line. Okay, it's like a string. Okay, if you don't want to hear about curve, it's actually a string. Okay, so let's draw this curve here. So 3 over x, right? So it should be something like this. Okay. Well, this is y equals to 3 over x. So here's x, here's y. And then at the point 3, 1. Is 3, 1 inside my curve or not? So if you put 3x equals to 3, 3 over 3 is 1. Okay, so it's actually one of the point in my curve. So it is in the first quadrant in particular. So maybe here. So maybe I need to draw my curve lower. Yeah, like this. Okay, so you want to find this tangent line here. Okay, but finding tangent line, you are finding the limit of secant. Okay, like what I told you just now. Okay, so you need to find the gradient first. So what's the formula? So m tangent is equals to limit of h go to 0 of fa minus fa or fa plus h. Okay, let's fix one. Let's fix this one. Okay, let's fix this guy here. Easy. Okay, otherwise the one I show you just now have a minus sign. Okay, so let's fix this one. Fa plus h minus fa over h. Okay. It is equivalent to what I have just now. Just now I wrote this. If you notice. Okay, it's equivalent. It's just the different by a minus sign. Okay. Yeah. Okay. So you know how to do this? You know how to do this? You just substitute. Okay, you just substitute your f. So first you substitute x3 over a plus h. And then the second one, 3 over a. And the last one is h. Okay, simplify this. Can simplify or not? How to simplify this? So what's my a? Is my a fixed? You know what's my a now? Yeah. What's my a? 3. Okay, so 3 is my a. Okay, so when a equals to 3, okay, so we should replace all the a here. Okay, h is the one that you put limit on. Okay. Okay, so how to simplify this? Anyone got idea? What's the simplified form? Do you know how to do the simplification? What should you do first? What should you do first? Well, I mean, one way is you combine the fraction first. Okay, how to combine fraction? You make the denominator the same. Okay, so one way you could do was you make the denominator the same first. B times 3 plus h. Okay, divided by h. Okay, where's my h? So can we simplify this further? Huh? So you divide, right? So this a divide b divide c. How should we deal with it? It is actually equivalent to. It is actually equivalent to multiply by 1 over h. Okay, so you can put the 1 over h into it. Yeah, not. Okay, so how to simplify it? Can we simplify further? So actually you can see that all of them have a factor of 3. So they can cancel. And then 3, okay, let's do it step by step so that people don't confuse. Okay, so we get this. Okay, then continue. Minus h over h over 3 bar h. Good. So we got some h cancelling out. Okay. So altogether we get minus 1 over 3 h. Does this limit exist or not? It is continuous, so you get 1 over. You get 1 over 3 minus 1 over 3. Good. Okay, so this is the gradient. But question is to find the line, equation of line. Okay, so you have gradient. Do you know how to find a line? How? What's the formula?
Y is equal to x.
So wait, let me put equation of line first, or line equation. Line equation. Y equals to what?
F at x, fx plus f derivative x, x minus x0.
X plus.
F with a like derivative make like symbol. Like it's our gradient.
Okay, let's put it as gradient then. M
Then in the brackets
bracket
x minus our like a,
X naught
and then
plus
x not
Y naught.
like that.
Okay. Yeah. So well, I mean, if you rearrange this is the y1, y2 over x1, x2 equals to gradient, right? Okay. Okay. But the point here is this y naught and x naught are fixed point. Okay. Y and x are any point with them. Okay. All the other the rest of the point. Okay. So we got the x naught, y naught here. So what's our x naught, y naught? Set x naught, y naught to be 3 and 1. Okay, and our m is minus 1 over 3. Okay, so all together we get y equals to minus 1 over 3, x minus 3 plus 1. Okay or not? Okay, so this x naught and y naught is very important because you could imagine that this line here have the gradient of minus 1 over 3. I can also simply put another line here as well. Y equals to minus 3 over x. This is also a gradient with minus 1 over 3. Understand or not? Okay, so the x naught and the y naught kind of like shift this line, okay, to the right tangent line. Okay, so far so good. Question?
No question.
Okay, you got no question about the rest? Question? Feel free to ask. I might make mistake also, so don't think that whatever I say is correct. Okay, so digest what I say. Okay. Any question? Question? Nope. Okay. If not, we'll go to the next next meaning of derivative. So this meaning, you see that this is the same limit here. Okay, this is the same limit. You recognize this, okay? But we're gonna interpret this limit differently. So let's say this f here has a special property, which is what we call a position function. Okay, position function. So meaning if you look at the graph just now, right, you should think of this graph is a movement of some particle. Okay, movement of some particle here. Okay, so you should think of this x as a time variable. When x go far, this pebble or this ball, okay, move along this curve. Okay, move along this curve here. Okay, then how do we compute the velocity? Okay, the instantaneous velocity. Do you know what? Do you understand what the instantaneous velocity is? The velocity you compute in physics, you take the n final displacement minus initial displacement divided by the time. That one is the average velocity. Okay, that's the average velocity. The instantaneous is the one that given by this tangent line. Okay, at this point, okay, without computing the final displacement minus initial displacement divided by time, what's the velocity at that? It could be done using this tangent. Okay, this this limit of secant gradient. Okay, because we are looking at the we are looking at the what? At the limit of the average velocity. Okay, we are actually looking at the limit of the average velocity because this is average, right? final displacement minus initial, okay, divided by time. So this is the limit of the average velocity. It's the instantaneous velocity. Okay, at that point, what's your speed? Okay, let's see. How should we discuss this question? Okay, let's discuss this question. Maybe we don't compute finish, but I'll tell you how to start it. Then you can finish the calculation yourself. So suppose the ball dropped from the upper observation deck of CN tower. I think it's the CNN. So you just draw a tower like that. Okay. And then a ball will drop from here. So this tower is like 490 meter above the ground. So maybe the height is like this. Meter. Where its position from its starting point is being given by the function for t equals to 4.9 t squared. Okay, so what is this? This is the position of this function here. This function should be the displacement function for this ball. Okay. Okay, so here is ft equal to 4.9. Okay. So we think of this displacement as a gain of displacement, as a gain of displacement. Okay. It's a gain from displacement. Although the direction is negative, right? Okay, so it is positive, but or you could actually consider ft equals to minus 4.9 t squared. It's fine, okay? Okay, depend on how you want to view this. So what's the velocity here? What's the velocity of the point after 5 seconds? So what we're gonna do is we find v at t equals to 5 seconds. Okay. So in particular, what we're gonna compute is h equal to 0 when f is 5 plus h minus f5 over h. So we want to find the velocity after 5 seconds, maybe somewhere around here. 5 seconds maybe. Okay, so you need to take all the tangent. Okay, you need to consider all the tangent, the limit of all the tangent. Okay, hopefully you can see what I'm trying to do here. Or maybe a tangent secant or something like this. Okay, makes sense. Okay. So if you go through some calculation, right? I think, okay, let me at least write down what's the function you could get. So it's 49h plus 4.9h squared over h. Okay. So this one you can easily compute the velocity, which is 49 by 49 of mx. Okay. Well, if you learn some physics, right? Because this ball is downward, this velocity should be negative. Okay. But you should see that this negative sign here, this positive sign should be coming from your function. Okay, your function is already positive. So that's why this is positive. Okay. One way to go around this is you can put your function as negative. Okay. Then you already come out with a negative velocity because your displacement is going downward. So when you get a very large negative number, actually you are gaining some, I could say, work done, but it's in the negative direction. Okay. So make sure when you deal with these kind of real life problem, physics problem, these plus minus sign, you should take care yourself. Okay, as long as your final answer makes sense. Okay, for instance, why this makes sense? Maybe it makes sense after you plus downward here. something like that. So you need to make sure that you know this positive sign is for downward or upward. That's all. That's it. Okay, that's the point. Okay. And how fast does the ball traveling when it hits the ground? What do you think you should do? Sorry? Huh? Good. First thing is you find out when it hits the ground. So what does it mean by hitting the ground? What does it mean by hitting the ground? Your displacement is equal to the height, 490. Okay, so I think this is another reason why they set this function to be positive. If you set this function to be negative, then this displacement, this height should be becoming negative also, because your direction is negative. Make sense or not? So that's why people set this as a positive, so that easy to describe this situation. Okay. So the first thing is you set 4.9 t squared equals to so let me quickly write down first. So set 490, and then you will find that what's the t you get when you're hitting the ground. And actually, it's plus minus 10 seconds. Could it be minus 10 seconds? Okay, unless your clock go backward. Okay, so it's a 10 second, then you go and find what is v at t equals to 10 seconds. Use the same method. Okay, so if you compute it, it's actually a 98 mx minus. Okay, makes sense? Okay, try and go back and do the calculation. Yeah. Okay, next we finally define what is derivative. Exactly, we define using the same limit of the secant, but at the same time we can replace this h go to 0 by some other x. Okay, so when h go to 0, it just means that it just means what? It just means that this a plus h is going to a. Okay, so I can replace a plus h by this x here. Okay, so where is my note? Okay, so you can set a plus h equal to x like that. Okay. So in this case here, h equals to x minus a. So when h go to 0, meaning x will go to a. Okay, so these are the two equivalent ways to write. Okay, these two ways I think is good that you can. It's good that if you can remember them. Okay, these two are the same form. Okay, either a plus a bit of distance or other point than a, and then move to a. Okay, so let's do one exercise and then we can finish for today. Okay, so if this limit exists, we'll say that f is differentiable. Okay, so this is the next notion. So we have notion of continuity, and then now we have a differentiability here. If this limit exists at a, it is differentiable. Okay, so let's compute this. So we have fx equals to x cubed plus 7x. So if you just follow this formula, f prime a. So what's the definition? Okay, let's use the new definition. Okay, you can try and use the second one. Okay, see you get the same answer or not. Now we use the new one. Okay, so the new one is fx minus fa over x minus a. Okay, so you just do the appropriate substitution. Yeah? So fx is x cubed plus 7x minus a cubed plus 7a over x minus a. Okay, and then you continue. So if you continue, what do you get? X cubed plus 7x. Okay. Let me rearrange. A cubed. So here is a minus sign plus 7 of x minus a over x minus a. Okay. So what happened? If you do the usual substitution, the stupid way, if you put substitution, a cubed minus a cubed 0, a minus a 0, a minus a 0, 0 over 0. What do? Close the paper, throw away, go and sleep. No, what do? What should you do? You should factorize actually now. Okay, you can do factorization. Do you realize or not? So here you got x minus a. Here got x minus a. Here got x minus a. There is. You should do a long division here. Okay, you should do a long. Do you know what's long division? You know? Don't know. No idea. Never thought with this term before. Long division. So use x minus a to divide this x cubed minus a cubed. Never learned before. So multiply x squared, you get x cubed minus a x squared. It's like how you do division for a number, but you do it for polynomial now. Okay, so in this case here you get what? Plus ax cubed minus a cubed, and then you can multiply a squared to get ax squared minus a square x, and then you get this. So you multiply a square again, so you get a square x minus a cube. So you cancel everything. Never learn. Never learn. Can understand what I say? What I doing? Can I say what I doing? Understand? Can So this is like your, how to say? You also divide like this, right? Okay, maybe I divide like this, maybe bigger a bit. So what do you do? 4, 1, 4, and then take away 30, right? Like that. And then you, sorry, I'm stupid. So here I get this, right? And then, oh, luckily I can divide finish. Okay, so this is the same. So you multiply x squared to this, and then you get this, and take difference, and then continue. Okay, so if you can factorize, then you can finish here. If cannot factorize, here cannot finish. Okay, so in this case, what we get here was limit of x to a of x minus a times x squared plus ax plus a squared. Okay, so that we got all the same factor, which we can simplify. Okay. Okay. So what's my final answer? Quickly get the answer and then we can finish. So here we get the x squared plus ax plus a squared plus 7. So now this is a perfectly good polynomial. Okay, so just do substitution. So how many a squared you got? You got 3a squared. Okay, plus 7. Okay, that's it. Okay, any question? No, about the rest? Question? Good. So this long division, one of the very important tool you need to learn. This is the long division between polynomials. Okay, if you can finish this division here, then that means you can factorize it. If not, you cannot. Okay, this is similar to your number division. If you can finish this division by nothing, then that means that 700 is equal to 4 times 175. Otherwise, you have a remainder. Okay. Okay, so in that case, see you on Friday. Okay, you too. Yeah.
Can I use this way much faster?
What do you mean? Where? Let me turn off first. I think we should talk outside because the lecturer coming.